I'll begin with a word of prayer. Dearly Father, we thank you for this day. And Lord, I thank you for the students. Just pray that you just guide our thoughts today. Help us to just understand a little bit more about Lie groups and the Baker-Campbell-Hausdorff relation. Lord, in your name I pray. Amen. Okay, so we're just going to try to follow along in here. There's a lot of really interesting calculations in this part of the book. I read through it earlier, and I think we'll be able to follow a fair amount of it if I don't get too tired. So I'm doing my best to work on that. I think we're going to make it though. And so I thought this first thing he next does, theorem 3.1, as I mentioned, we're in the groups, the algebras, representations, and elementary introduction. Something here. Something is it's a typo, something like graduate. It's a typo. Theorem. So here's the theorem 3.1. Suppose you've got complex n by n matrices and x and y commute with their commutator. X and y elements of n by n complex matrices, and you have the following conditions. The commutator of x and xy is equal to 0, and the commutator of y and xy is equal to 0. This condition, for example, is met by the Heisenberg group, the algebra for that. Because the algebra for that is like the 3 by 3 strictly upper triangular matrices. So when you multiply two of them, you get a strictly upper triangular matrix with a 1 in the upper 1, 3 component. And then when you take that with anything else, it goes to 0. So you get this condition, for example. But the method of proof here is interesting, okay? Then, well, I guess we haven't really said anything yet, have I? Like here's the theorem, here's conditions. Aren't they interesting? No. Then, here's actually the theorem. E to the x, e to the y is equal to e to the x plus y plus 1/2 x commutator y. So basically this is a special case of the Baker-Campbell-Hausdorff relation. Like we proved last time with a plus dot 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 dot, this is true, right? But we didn't prove that all those higher terms are in fact nested commutators, right? In fact, it took a fair amount of finagling just to see what we already had was 1/2 commutator of xy, right? Like, or AB, whatever it was. So this is like a pretty legitimate result if we can get this. This is an improvement on what we did last time. So we'll follow Brian Hall's argument here. So he says, we will prove the following identity. What he wants to do is he wants to prove that e to the tx, e to the ty So if you were to ask me what this calculation is most like in advanced calculus, I think I probably would tell you it's probably most like those things we studied with doing an integral by introducing a parameter, right? So it's like the identity we want has t equals to 1 here and here, right? So it's like he's sort of looking at looking for a parameterization of the identity in some sense. Because once you have a parameterization of the identity, what does it bring you into contact with? Well, the main point is calculus.
Right.
Yes. Yeah.
Didn't we do certain types of special integrals where we had to introduce a t, and then we did like...
Yeah.
Oh.
Yeah, I'm saying this is a lot like that technique, right? I mean, it's kind of in that same sort of wheelhouse, I guess. Now, his first move is, we're assuming that the commutator of x and y commute with x and y, right? So this would be equal to what? E to the tx plus ty times e to the t squared over 2, commutator of xy. I can do that because remember, if we have commuting matrices, the law of exponents does hold for the matrix exponential. I guess I haven't proved that, but you can prove that. That's not that hard a thing to prove. Okay, then we know that the inverse exists for everything. It's just the minus thing. So I bring it to the other side, and I find the equivalent identity, e to the tx, e to the ty, e to the minus t squared over 2, commutator of xy, equals to e to the tx plus ty. All right. So this is an equivalent identity to the one we have. Obviously, if we have the one that I'm about to underline in some color that I find, apparently pink. So if we have the one underlined in pink, this guy, right? If we have star, then it's pretty clear we'll get this star star as an equivalent identity, right? And if you put t equals to 1 in star, then that's exactly the theorem, right? Agree? Okay. So what he says is to just do some name calling. So what we're going to do is call the left-hand side of this a of t, and we'll call the right-hand side b of t. All right. So notice from differentiation we have what? dB dt is equal to what?
X plus y times b.
Right. Or you could write, in this case, you could have pulled the derivatives out on the other side, right? And let's do that since he does that. When you're differentiating the exponential, you can either bring the chain rule either to the left or to the right. It's an identity. All right, so that's a differential equation that dB, I mean, x and y are fixed here, right? They're fixed. So this is a differential equation that B satisfies. What's its initial condition? What's B of 0? Yeah, let's see. Right, the identity. What's A of 0?
I guess it should also be that.
Yeah, I think A of 0 is also a good
Right, yeah.
identity. So if we can show that A satisfies the same differential equation, then we'll have, by existence and uniqueness of systems of differential equations, that A and B are equal. So that's that's the argument. And so I was reading Stilwell's naive lead group theory. I wanted to look back now that we're here. I wanted to look back at his proof of Baker-Campbell-Hausdorff, and one of his criticisms is that all the other proofs in these kinds of books, they are based on existence and uniqueness. And yeah, okay. This isn't Baker-Campbell-Hausdorff yet. It's still a baby step, but okay, let's get to it. So we need to differentiate A, right? So you got d a dt. d a dt is what? It's, let's see here, e to the t, so it's the triple product rule, okay, so e to the tx, x, e to the ty, e to the minus t squared over 2, xy, plus e to the tx, e to the ty, y, e to the minus t squared over 2, xy, plus triple product rule, right? E to the tx, e to the ty, e to the minus t squared over 2, xy. What's the derivative of the inside argument in the last term, though? If you differentiate this with respect to t, you get minus t Yeah. Minus t commutator of x and y. All right, yeah. So it's nothing more than the FGH prime is F prime GH plus FG prime H plus FGH prime identity. All right. Now it takes a little bit of finagling. His point next is that xy commutes with, of course, this and that commute, right? So you could, rather this and that commute. So the second, actually this one, the second term on the right can be rewritten as what? We'll need another marker, just a second. Let's see here. So this one we can rewrite as what? This and that commute.
So
Right?
it'd be A Ty.
Oh, really? I wasn't thinking about it like that, but okay. Oh yeah, once I flip these, then yeah, you're right. So this is the same as AY, right?
Yeah.
Oh, A of TY. I see what you're saying. Because you can flip these. Okay. It says the first term.
You're allowed to flip those?
Well, we're assuming that this and that commute.
Okay.
So.
Because exponential is just power, so.
So then,
It's 4:00 p.m.
so can we then say it's equal to AT times x plus y plus A to t commutator?
Just a second. And then he picks on the first term. He says x doesn't necessarily commute with. Now there's something really tricky he does for the first term. I'm not sure that this is a helpful step. The verdict's not out on that yet. It may be, may not be, I'm not sure. I mean, it's definitely a legitimate step. I think that's a good observation. So he points out here, and this isn't directly useful yet, but he points out if you have x e to the ty. Again, this is, I'm not continuing, I'm just saying it's useful for that, okay? Then he's like, okay, so what you can do is add in the identity. Right? Now what have we done here? That's conjugation, right? That's conjugation by e to the minus ty. In other words, that's e to the ty times the big adjoint of e to the minus ty acting on x. But what did we prove? There's a connection between the little adjoint. So this is exactly the place where you want to write things in terms of the little adjoint because that's nested. I mean, using the little adjoint is coming into contact explicitly with nested commutators. That's what the little adjoint does, is it makes nested commutators. So this guy here is e to the ty, and then we've got the exponential of minus t times the little adjoint sub y excuse me, of x. Actually, it's like this. This is an operator. Like, so the exponential of minus t and y is understood to be an infinite series of operators. All right. So I guess
The little adjoint is just the well, no, I guess not.
right.
But yeah.
Yeah. What is this? Right. So I'll write it over here. E to the minus t adjoint y acting on x is what? It's x, right? Minus t times a little adjoint y acting on x, right? Plus 1/2 t squared add y of add y acting on x, and so forth. Now what is that though?
After
This is just what? I could write this as plus t times xy if I wanted just to flip the commutator, right?
right.
I'm not sure that's helpful or not. But this
It's gonna
already,
be 0.
see this is already 0, right? Because this is like the commutator of yx, which of course is minus xy, and then you're taking the commutator of y. See, Bradley, you're taking the commutator of y with this input. Well, that's like commutator of y with the commutator of x and y, which is assumed to be 0. So this infinite series just truncates to these guys. And, all right, so then what? So then we can go back and we can simplify the term. Let me do it in a different color. The first term we can simplify as what? It's really just what? So we've just shown that like this is that, right? And let's see here. So we have x e to the ty, which is right here, right? So we have that this first term is actually e to the tx times what? Times x plus t times the commutator of xy, right?
Times e to the negative t squared over 2.
Oh yeah. Right, now apparently if we just put it all together we should get what we want. Let's try to see it. Let's see here, so is there there should be like an AX in here, right? What was A? A is e to the TX.
Oh wait, you also need an e to the ty. What you wrote in blue would be e to the tx, e to the ty times.
So I should have that before this, right?
Yeah.
So like e to the TX, e to the TY, that's good.
Mm-hmm.
See, because then if you look at it from the first term, we also have, yeah, okay, I see it. If you multiply out this times that, right? That in total gives me these,
e to the ty.
yeah. So you see what we got then is we've got terms we want, which is a A of t, right, times x plus y. And then everything else must somehow cancel. All right. So somehow the terms I'm about to underline in green, they got to cancel. Got to cancel. So this one and this one, right, somehow cancel. Oh, well, duh, they cancel. Look, it's e to the tx, e to the ty, commutator. The point is, these commute, right? I mean, like, the fact that the commutator is second and it's first over here, that's immaterial. These commute, so. Yeah, the green terms cancel, and you're just left with that. Therefore, we've shown that A of t and B of t both satisfy the same differential equation, which, by the way, is obvious to which differential equation you're looking for is already immediate. Like, as soon as you write down B, which differential equation you're looking for here in this argument is just manifest. That differential equation wasn't hard to find for B, right? It just popped out. So, yeah, there you have it. And this is really our first, contact with this, how the big adjoint and little adjoint work together to actually make use of that, like, nested commutator identity. It's explicitly how it goes down. Now his theorem, the rest of the stuff in this section I don't want to write down, I just want to talk about, okay?
Okay.
So his theorem 3.2, put t equals 1, you got the theorem. Okay, so theorem 3.2, he says let H denote the Heisenberg group, and H is Lie algebra. Let G be a matrix Lie group with Lie algebra frac G. Phi, Lie algebra homomorphism from frac H to frac G. Then there exists a unique Lie group homomorphism, phi, from H to G, such that capital Phi of e to the x is equal to e of little phi of x for all x. And so basically the proof is, it uses the fact that the Heisenberg group has a bijective exponential. And so he's able to defines the group homomorphism by exponentiation of the algebra homomorphism. Phi of a is e to the little phi log a. And then he's able to, because the Heisenberg group satisfies that the commutator of the commutator with either element is 0, he's able to use the Baker-Campbell-Hausdorff relation to prove the group property for the homomorphism so defined. And that's it. Okay.
That's the definition of the Heisenberg group, just that it's commutator to commutator.
No, well, the Heisenberg group is back in chapter 2. I haven't talked about it, but yeah, it's goodness gracious, where's that thing? Man, if memory serves me correctly, it's not actually a matrix Lie group, which is kind of funny.
141, the Heisenberg group.
Okay, well, I was wrong. So all 3x3 real matrices, the group strictly upper triangular with 1s on the diagonal, right? And then if you differentiate that thing, you end up with just non-trivial upper triangular. So something Lie algebra looks like that, strictly upper triangular 3x3 matrix. Basically the deal is, if you take the commutator of two such things, you only have a non-zero 1, 3 element. Because like taking the commutator of two strictly upper triangular matrices involves taking products of two such matrices, which is again more strictly upper triangular. Like every time you multiply one of those things, it pushes itself up off that super diagonal and more into the corner. And so, yeah.
So you just get the top right, basically.
In fact, if you think about it, if you wanted to create a Lie algebra of matrices such that the commutator of the, and like one more, if you wanted that to be non-zero, but then the commutator of commutator of commutator, did I say that right, was 0? If you use 4x4 strictly upper triangular matrices, like the first product shifts it at 1 up, and then you can kind of just play this game until eventually you get to the, the 1 and the, so. if you're looking for ways to create examples like that, I think strictly upper triangular matrices are the way to go. I think I'm digressing. Fun to think about that. Okay, that brings us to the general Baker-Campbell-Hausdorff formula. And the argument here is slippery. So he starts by looking at this function, g of z. He's like, look at g of z is equal to log z over 1 minus 1 over z. He says this function is defined and analytic in the disk. Modulus of z. I should use this notation in complex. It's a nice notation. I never use it though. You know, I should embrace that notation. It's so much less writing. Oh well, too late. I'll delete this for now. That is centered at 1, right? So like if I was to draw it, it's like this, right? Oops, that was supposed to be a circle. Sorry. Anyway, this function is defined and analytic. Now that, if that's the usual logarithm that's got, you can, well, depends on what you mean by logarithm, right? So certainly you can look at the principal logarithm, which has a jump discontinuity on the negative real axis, right?
Mm-hmm.
And so you can define that to be analytic there. It's just a half plane. You can pick a branch of the logarithm to work there. Sure, why not? It's analytic. And so what that means, guys, is that there exist coefficients. All right, there exist coefficients a sub m such that this is expressible as a power series in z minus 1. M equals 0 to infinity. A sub m z minus 1 to the m. Okay, so there exist these coefficients, these constants a sub m. It doesn't really matter what they are, they exist. All right, you can work them out. And so, if you have a matrix or operator A, and that operator has a minus I less than 1, can define, what can you define? Well, you can define g of A in the same way. So use the same coefficients as we just discussed how we would derive, although we didn't actually do it. For that function up there, these a sub m's, a minus I to the m power. And that brings us to the integral form of the Baker-Campbell-Hausdorff relation. And let's see here, I guess I'm going to state it over here. Keep it out of the way. Theorem for all x and y in Cn by n, and it's actually not for all, it's for all these sufficiently small. This is not a global result. The Campbell-Baker-Hausdorff series diverges for matrices which are not sufficiently small. Okay. Here it is. Well, log of e to the x, e to the y is equal to x plus the integral from 0 to 1 of g of e to the little adjoint of x times e to the t little adjoint of y acting on y dt. Sorry, I had to run around the corner. Yep. Now, if you're like me, your initial reaction to this is that doesn't look anything like the Campbell-Baker-Hausdorff relation that I know. Right? so what's going on here? First of all, g of the exponential of the adjoints makes sense because the exponential of the adjoint is a linear operator, right? And for x and y sufficiently small, that means that the exponential of the adjoint is pretty close to the identity, right? That makes sense to you guys? I mean, if you think about what this is it's this like we were starting to write one of them down here, right? Like it's the, just the thing again, plus one adjoint, plus the adjoint of the adjoint, plus a scale factor times the adjoint of the adjoint of the adjoint, and so forth and so on and so on. And as you see, you end up picking up like multiplicative factors of x and of y for these guys, right? And so if x and y are small, then the series is also, these guys are getting. It makes sense that these would be small, and so that this would be not big. So in other words, this series is not big. X is close to 0, so the whole thing is close to. This thing is close to being 0. So basically, this is just basically approximately dominated by x. In other words, the exponential of the adjoint for a very small matrix is very close to the identity. All right. That's important because, remember, if the operator minus the identity is less than 1, then we can define this. So certainly if the a were the thing we're feeding in here, this is like the a, that needs to be close to the identity, otherwise the requisite coefficients don't converge with respect to the operator norm. Alright, going on. So, what happens if x and y commute? I think if x and y commute, that's just
the left-hand side just going to be x plus y, right?
it should, yeah, well, exactly. The left-hand side will be x plus y. How about the right-hand side? Can you see that's also x plus y if x and y commute?
X and y commute. Oh, isn't that just all of that e to the add stuff just goes to e to the 0, correct?
Oh, right. Actually, those are strict. It's just straight up the identity, right?
Right.
I mean, it becomes g of I suppose. And if I look at I think it just leaves a sub 0, which must be 1 if we study this, okay? And so then the integral of 1 dt is just t. Well, we have this y rides along, so this integral must produce a y in the case that x and y commute if you work through the details. Okay, I will read you what he says about this. This is formula 3.6. He says, is admittedly horribly looking. However, we are interested not in the details of the formula, but in the fact that it expresses log of the product of the exponential of x and exponential y in terms of the Lie algebraic quantities add x and add y, right? And he mentions that Jacobson actually has an explicit direct proof that you can express log e to the x times e to the y in terms of commutators. It's a C proposition in section 5.5 of Jacobson, 1962. Come on, this is not the approach we will take. Okay. Okay. All right, let's not stop talking about what we're not going to do. Let's do what we're going to do. So corollary 3.4 is our next thing to do. And I may regret that. Oh well, what's done is done. You know what the G is. If need be, I'll put it down again. And at first glance through this, I was like, oh, this is all just technical bluff. But there's a lot of calculations in these proofs that are interesting in and of their own right. So it's more than just the end result. Like there's calculational techniques which I think are good for you guys to see, and so that's part of the reason I'm doing this, not just for the sake of doing it, although there's that. 3.4. Let G be a matrix Lie group and little fractates Lie algebra. All right. Suppose that you have a Lie algebra homomorphism, little phi. It's a mapping from frac G to n by n complex matrices. This is a Lie algebra homomorphism. All right. Then, for all sufficiently small x and y, so for x, y small enough, in G, the log of e to the x, e to the y is in frac G, and punchline phi of the log of e to the x, e to the y is equal to the log of e to the phi of x, e to the phi of y. This phi is a slippery character, isn't it? Finds its way inside and outside of logarithms just like that. He says this theorem uses the same reasoning as in 3.3. What was 3.3? 3.3. What was 3.3? I don't know what 3.3
This
was.
one you wrote on the other part. This one we just looked at, right?
Yeah, it's just the log form of the.
Ah. Oh, that's what we did last time.
The 3.3.
Oh, is he looking at a different equation?
Yeah, that's the 3.3 we did last meeting.
Did you do 3.3 last? Probably just did.
That was the explanation for why the Baker-Campbell-Hausdorff formula is relevant, as it says that the
Over on 64.
as it relates to the construction of the Lie group homomorphism from the Lie algebra homomorphism, which is the larger goal of
It basically
of
says
all
all that
here.
stuff.
Yes. Let's see here. Where was I? Lost my wrong page. Wrong page. Ah. Okay, so let's see here. Let's work our way through this proof here. He says if x and y are in the Lie algebra frac G, then add x and add y will leave G invariant, and so will that makes sense. Right, I mean, if you're calculating a joint of x of, let's say, G, and a joint of y of G for a G and frac G, right? Then what are these? These are commutators of I want to say they're commutators. I want to say, well,
Invariant means it maps onto a subset of itself.
yeah, it says that G should map to G. So like, this should go back to G again. I mean, I think that's true because this should be the bracket of X with G and bracket of Y with G, which is again in G because G is Lie algebra. And we're assuming X and Y are in G. Frac G, I should say. And then likewise, so will the G function of the exponential of the little adjoint of X and little e to the t adjoint of Y. Right, this acting on Y will again be in frac G, I think. So he says thus, whenever formula, this is formula 3.6. He says whenever formula 3.6 holds, log e to the x, log e to the x times e to the y will lie in G. Oh, okay, because if this is in G and that's in G, then this is in G. Alright, so he's like, if you have that, it remains only to verify 3.7, which is this thing. And I think that's what we're about to set out to do. He says the idea is that little phi is a Lie algebra homomorphism, then it will take the big messy expression involving the little adjoint and x and y and turn it into the same expression with x and y replaced by phi of x and phi of y. Alright, let's see how that happens. I don't need this anymore. That was just a motivating comment to say, once we prove 3.7, then this automatically falls into place, I think. Well, it's not. There's more to it, I think. Anyway, I mean, this is a corollary, so it's built off this in some way, and that's eventually proved in the next section, the Baker-Campbell-Hausdorff, as it's called. Well, you know, again, this is only Baker-Campbell-Hausdorff here. More on that as we go on. Make sure I make sure I leave enough time to talk about the big picture in here, because once we get past some of the stuff, there's still more to say. Just words, not math, you know. Okay, so we have phi of yx is equal to what? Phi of y, phi of x, right? That's what it means to be a Lie algebra homomorphism. And he points out that that also means what? You can restate that in terms of little adjoints how so? This is phi, right, of the little adjoint of y, right, acting on x equals to what? Little adjoint of phi of y acting on phi of x, right? And if you look at the ASIC, and then you can bump that up a notch. More generally, you have phi of the n-fold application of the adjoint of y acting on x is the n-fold adjoint of phi of y acting on phi of x. Then what's he do? No.
This is merging.
What's that?
Does he differentiate?
Differentiate? No. Actually, definition of the exponential. So, I guess you could look at that as, in some sense, you could look at that as just differentiation if you're very open-minded. Let's see here. I'm not sure my mind is that open today. Let's see here. Maybe. I don't know. Let's see here. X. Okay, so that, right, is... Now, what he's doing here, I'm going to put an extra step in. This is phi of what? The sum, m equals 0 to infinity, right? Of t to the m over m factorial, the adjoint of y, m-fold times applied to x. And then what he's doing in the next step is he's pulling the sum out. But this is a homomorphism. So setting aside some analysis here perhaps, m equals 0 to infinity, t to the m over m factorial, phi of the adjoint of y to the m-fold power acting on x, right? But now we can use the identity, right? We can use this guy to trade this, right? For that. Agree? So. So it's what? It's the adjoint of phi of y m-fold applied acting on phi of x, right? But this, right, is exactly the exponential of t times the adjoint of phi of y, right? That operator acting on phi of x. Now, you guys tell me if you can understand his similarly comment. I'm not sure I understand it yet. You guys explain it to me. So he says that it like similarly follows that phi of e to the adjoint x, e to the t adjoint y, acting on y, is equal to e to the adjoint phi of x, e to the t adjoint phi of y, acting on phi of y.
These adjoint functions commute with each other.
No. I don't believe so. But that should be understood to be the composition of operators. So it's like a... I mean, so I guess it might be...
The two things that are underlined in green, couldn't you do the same equivalence with this his new one that he introduced here, the e to the add x, e to the t add y.
Elaborate.
So the phi of add y and x, the green with the one bar underneath it.
Mm-hmm.
You could do the same relation with this what he has here, the add x t add y, through the same logic that you got there in the first time.
Oh, I think you're right. So like, just basically look at this as reorder the composition so that it's this of that, and then do exactly what you're saying. So you'd have
Oh yeah.
e to the t adjoint phi of x on all that, and then all of that you apply it again.
Mm.
So it's twofold applications of that. Exactly. Yeah.
We're doing the same thing with
Phew,
summation.
man, I'm glad you guys figured it out. All right. All right. So then he's like, great. What's his next move?
Knight to e4.
What's that?
I said knight to e4.
Knight to e4. He's like, assume x and y are small enough so the Baker-Campbell-Hausdorff formula applies to x, y, and also to phi of x and phi of y. Then using linearity of the integral and reasoning similar to that above, we have phi of... Okay, so I guess we're basically... Alright, so the idea is we've got these identities for the Lie algebra homomorphisms, right? And so our next move is just to go from log e to the x, e to the y equals to x plus the integral from 0 to 1 and g of e to the adjoint x, e to the t adjoint y acting on y dt. Feed this, act on, I should say, apply your Lie algebra homomorphism, which goes from where? From frac g to little g ln c, whatever. And that will give us phi of the log of e to the x, e to the y. That's just the right-hand side of the BCH identity, right?
No, he's not assuming any of this is true, right?
He's assuming that, is this a corollary to the BCH? So he's assuming the Baker-Campbell-Hausdorff is known. That's proved in a later section.
Okay, but he's not assuming that.
No, he's assuming that.
He is assuming.
That this is a corollary to that. I misspoke earlier.
Oh, there's okay.
Yeah, that's my bad. So we're actually using this to get that.
Okay, that's fine.
And so start by writing that. Then you take the Lie algebra homomorphism of the BCH. That gives us this, but it's also equal to g of x, right? Plus the integral from 0 to 1 of g. Now, g is expressible. G is no different than an exponential in some sense, right? You should think of g as being a weird exponential. It's just a power series of operators. So basically the point of these derivations is that the Lie algebra homomorphism naturally like filters through those. So in the same way that we were able to take phi from the outside to the inside, same calculation pretty much allows you to do that up here and get, where was I? Oh, come on. Oh, now he's actually, well, fine. Thanks a lot. Now he's got the details that I have erased. Great. Integral from 0 to 1 And you've actually got the power series for the g, which is the sum m equals 0 to infinity. Alright? So here's like literally what I was just talking about. A sub m phi of e to the adjoint x, e to the t adjoint y. That's the argument of g, remember? Oh man. Stink. The point was g of a was equal to sum m equals 0 to infinity of a sub m a minus I to the m full power. And so he's just putting a equals to the product of these exponentials, right? Like it's e to the add x, e to the t add y, this stuff, minus the identity, the m-fold power of that, acting on y. Hey, hey, hey. And then we use the identity. Then we go down the same path we just went down, right? Which is that the phi comes inside, right? So the phi comes inside the exponential. And it changes the argument, right? Over here as well, right? And of course I'm still integrating, sorry. Bash, don't tell my Calc 1 students. I missed my DT. Shame on me. You won't tell them, will you, Daniel? Okay. Have I taught Calculus 1 since you took it? I don't know.
I don't think so.
I guess they don't trust me after that time. Alright, and then what? Oh, then you apply the Baker-Campbell-Hausdorff one more time. This, by BCH, is literally what? This is literally log
So do the phi of x.
of what? See, it's log of, you see we've got phi of x and phi of y replacing x and y in this identity. So this is literally log of e to the phi of x, e to the phi y. Bam. And there you go. That is corollary 3.4. Alright. Sorry, I should have skipped past that. That's not what I wanted to talk about. Dang it. Alright. Let me keep moving along here. Derivative of the exponential mapping, section 3.3, is full of really, really interesting calculational ideas, guys. So, here, let's follow along here. He's like, if x and y commute, right, then e to the x plus ty is equal to what? Well, it's just equal to e to the x, e to the ty, right? What if they don't commute, though? So, I mean, in this case, it's, his point also is that in the case they commute, if you calculate the derivative with respect to time of e to the x plus ty, what do you get? You can just pull the e to the x out, right?